Hey guys, this is 11.3 geometric sequences. So a geometric sequence, first of all, is a sequence that has a common ratio. In other words, we are multiplying by the same thing each time, like this, times 6 every time. So in a general form, that would be the first term times some number r. That's going to be our common ratio. We're going to call that r all throughout. And then the third term would be the first term times r again, so r squared. And then the fourth term is the first term times r cubed. So each term is going to be the first term times r to the term number minus 1, so n minus 1. So generally speaking, it's going to be whoops, hold on. Technical difficulties. Apparently I should have hit that button before I hit record. Where am I? Okay. All right, sorry about that. So in general, each term is going to be the first term r to the n minus 1. So notice that the very first term doesn't have an r, so we consider that as r to the 0. Second term's r to the first. Third terms are the second. So it's always going to be n minus 1. And that should not be a comma. They're being multiplied. Whoops. Okay. Anywho, that is our formula. Our explicit formula. Okay. So first of all, if we're given a string of numbers, we want to know if it's a geometric series. We just check the ratio and see if they're the same. So for this first one, you're always going to do the term divided by the previous term. So 2 divided by 1, 4 divided by 2, 8 divided by 4, 16 divided by 8, so on. So all of those are 2. So this is in fact a geometric sequence. And this one you do the same thing, 12 divided by 48, 4 divided by 12, 2 divided by 4. If we do that, we get a different ratio each time. So this is not a geometric sequence. This is a geometric sequence. So that's hopefully pretty straightforward. When you graph a geometric sequence, it's going to look exponential. But this one is not actually geometric. So these are the two from the previous example. This one is geometric and this one isn't. So even though this looks exponential, it's not. So you have to make sure you don't just look at it and say, oh, that looks exponential, so therefore it must be geometric. You actually have to check the points and make sure that they actually work out, because things can look geometric without actually being geometric. This one is, right? But this one, remember, the ratios weren't the same. So it kind of looks geometric, but it's not. So if you're given a graph, just make sure you check. You don't just look at it and say, oh, it looks exponential, therefore it must be geometric, because that's not actually exponential, just looks like it. So anyway, continuing on. So if we want the recursive definition, we can look at it this way, where it's the first term, say our common ratio was 4. First term times 4 gives us a second term times 4 gives us a third term. So our recursive formula, our recursive formula is going to be an equals the previous term times r. So pretty straightforward, just the previous term times r, and that'll give you your next term. So that's the recursive formula. And then if we're given the first term and the ratio, then we can write both our recursive formula and our explicit formula, and we can find the terms, obviously. So this one, they used the recursive definition. In other words, they just multiplied by -2 each time. So that would be an equals the previous term times -2. Or you could write the explicit definition, an equals 5, that's the first term, times -2 to the n minus 1. That would be the explicit definition. So recursive definition, explicit definition. And remember that when you're asked to write a recursive definition, you have to include the first term. So I'd have to write A1 equals 5, and then this to have the full recursive definition. And then A1 is already in the explicit definition, so we don't have to state it. Okay. So hopefully I'm not moving too fast. Hopefully this is all pretty familiar from Algebra 2, and yeah, it's not that different from arithmetic. It's just multiplication instead of addition. So we already talked about that. So again, you have to state what A1 is in order for it to be a complete recursive definition. And here's our exponential looking graph, so that's good. Writing R first is a good idea. I didn't do that in my example, but then you don't have to write it in parentheses, which is nice. Okay. So hopefully we know that when we're given an explicit formula and we're asked to find terms, we're just plugging in the term number into n, just like we did in the last couple of sections. So once you have your explicit formula and I want to find, say, A20, right, the 20th term, I'm just going to plug 20 in for n. So I'd have 18 times 2 to the 19, right, because n minus 1. So we're just plugging in, and there we go. That's the formula that I wrote down earlier. And if we are given two numbers and we want to find our formula, we just need to figure out what R is so that we can write our formula, and then we'd be able to find any term. It wouldn't matter what term they asked for, right? Once we find our formula, we can find any term. So I can use this form that I know and the fact that I have A1 and I have A4. So I can say, okay, A4 equals A1 times R to the 3. I know this has to be a 3 because it was n minus 1 and I'm finding A4, right? So this has to be a 3. This 3 is A1. We were given that. And then we are told that A4 is 24. So I can just plug in 24. So 24 equals 3R to the third. Divide both sides by 3. 8 equals R to the third. Cube root of both sides, R has to equal 2. How do we know that the 2 is positive? Well, in some cases we don't know. We kind of have to assume, which is annoying. In this case, however, we can be sure because we have an odd term and an even term, and they're both positive. If R is negative, then either all of the even terms will be positive and the odd terms will be negative, or all the odd terms will be positive and the even terms will be negative. Because when I'm multiplying by a negative number, I'm going to be switching back and forth between positive and negative every time, right? So if I have negative 1, I have 1 times negative 2 is negative 2. Negative 2 times negative 2 is positive 4, right? So I'm going to be switching back and forth between positive and negative. So the fact that I have and the fact that I'm taking the cube root as well. But I'm bringing this up because if these had both been odd, then I would be taking an even root, and I wouldn't be sure if it was positive or negative. So this whole spiel, you're probably like, well, we're taking a cube root, so why are you even questioning it? I'm questioning it because there are situations in which you would need to question it. And that would be if these were both odd or both even, then you wouldn't know for sure if it were positive or negative. With only this information to go on, I think you can assume positive just because that's generally the assumption that we make. But you might want to state that it could be negative, but you're going to assume positive. So if you're given, say, A1 and A5, right, then you'd have an even number here. You'd be taking an even root, and so you'd have that plus or minus you have to deal with. I think it would be enough just to state that it could be negative, but you're going to assume that it's positive. And then once you have R, then you can just write the formula. So R is 2, so you just put 2 here. So you get AN equals 3 R to the n minus 1, or sorry, 3 times 2 to the n minus 1. Remember 3 was A1. And then whatever term they tell you, you can just plug into that. Yeah. All right. So if you're writing a formula given just some numbers, you just need to find R. So you just divide one of them by its previous one to find R. Or in this case, it might be obvious to you that it's 5. You're multiplying by 5 each time. And then you use the formula we talked about. Yes, definitely want to talk about this. So I want to talk about hold on 1 second. Okay, sorry, I just wanted to check something really quickly. We don't actually have a word problem in the homework for this section, but I'm going to talk about it anyway because there will be in the next section. And so getting an idea is good. Okay, so we have students in a small school, 284 students altogether. And then we're expecting a population increase of 4%. So remember that when we have a increase, so you can think of this as an exponential type formula. When we have an increase of a percentage, we have to change that percentage to a decimal and add 1, right? When we have an increase by a percentage, we add 1. When we have a decrease by a percentage, we subtract from 1. So this is going to be a common ratio of 1.04, right? 4% plus 1, 1.04, and then we can just use the formula. So the formula they're using is A0, AN equals A0 R to the N, which makes sense if you think about it, because if we start with 0, then that would be R to the 0, which would be would not have a the R would go away, right? It would not have an R there. If it's R to the 0, that's just 1. So you'd end up with whatever the original was. So it's just kind of a way of rewriting the formula we've been using. It's not a different formula. It's just a rewriting of the formula we've been using. If that confuses you and you want to use the original formula, by all means, go ahead. I think this is just kind of honestly, I think it's complicating things, but I think that the reason they do this is so that when you're plugging in numbers later, since you're looking for the number of years since 2013, 2013 is year 0. It's not year 1. That would be 2014. It's year 0. So we are really starting at 0 in this word problem. So it just makes sense for the plugging in of numbers later if we think of 2013 as year 0. So we've shifted the formula to match the fact that we now have a 0 term, which we didn't before. We just started with 1. Because often in word problems, as we know from the many word problems we've done in previous units, we generally tend to start with 0 and then go from there. And so this formula reflects that. So when we're doing this subtraction here, we get 7, noting that we're starting at 0 instead of 1. Hopefully that makes sense. So we want to start at 0. And then we just plug into this formula. So this was the original amount. This is our multiplier based on our 4% increase to the nth power, noting that we are starting at 0. So we want to find the population in 2020 with 2013 being year 0. So we're just going to subtract the 2, so it's 7 years later. So 7 is going to be our n. Plug that in. We get approximately 374 students. Remember to round to the nearest student because it doesn't make sense to have a partial student. So that would be the answer for that. So the only weird, I guess, caveat with the word problems is that we're changing the formula to start at 0 instead of 1. Like that's really the only big deal here. Hopefully that helps. Let me know if you have any questions, and I will see you guys later. See you later.